thank you everyone, and thank you for the invite and the time to present here today. So my name's Paul Wright, working in the Optical and Quantum and Networks research team at BT Labs in the UK. And this, I guess, is now going back a little bit towards sort of the QKD networks and how we've taken sort of point-to-point QKD networks into multi-tenanted wider networks. So just to start off as a basic introduction, I think we've talked about this a little bit already, but quantum key distribution, or QKD, is typically a sort of point-to-point system for getting secure keys from one place to another. And it does that by encoding keys using the properties of quantum physics, such that any eavesdropping on the transmission system can be detected. The act of that eavesdropper attempting to intercept the stream destroys the quantum state. So typically we've looked at sort of QKD systems which have been deployed over optical fiber links, encoding keys onto a stream of single photons, as we've seen in some of the earlier presentations, using phase or polarization or any other sort of quantum property that can be interacted with. Satellite QKD systems are also possible. And so by sending a constant stream of new key material, two sites can then be used to encrypt data, and we can then update those keys regularly and keep them refreshed. So QKD system performance is measured normally using two sort of interconnected parameters, the first of which is the secure key rate, which is the amount of usable key material which is produced between those two sites, and the quantum bit error rate, which is the ratio of the number of errors in the transmission of the keys. In the event of an eavesdropper being present, that quantum bit error rate would start to increase, and there'll be a simultaneous decrease in the secure key rate. So that is what gives us that indication that an eavesdropper would be present in the network. As we've seen in an earlier presentation, loss is one of the main factors for determining that performance of a QKD system. In an optical fiber system, that loss equates to distance. Also, noise in the form of coexistence with other signals, such as sort of general classical signals, also has also on the same fiber has the effect of decreasing the key rate that's available. Also, the key rate of a QKD system is also dependent on the quality of the photon detectors and the process for privacy amplification to produce the final key material. The graph we can see on the slide here is shown from a Toshiba white paper, and looking at their system, and we can see how the key rate decreases as we start to increase the distance of the fiber link. But unlike the classical signals, as we saw earlier, we just can't amplify them classically as we've done with sort of standard data transmission. The laws of physics mean that we can't make copies, which amplification effectively is doing, without sort of destroying the quantum state. So taking that system and looking at how we extend the reach of a quantum network, the first approach might be the sort of trusted node architecture. So in this one, we read the quantum state, we process it classically, and then create a new quantum state to forward on in the network. Because we're going back to that classical domain, these nodes must be trusted sites, hence the name of the process, meaning we have to have secure racks in secure rooms. These types of nodes are used in quantum networks today, but they are typically just suited for specific tasks. So, for example, QKD, where we can relay keys using this approach, but may not be sort of possible for sort of more complex generic quantum computation. And we'll see how the QKD trusted node architecture works in the next slide. The other approach would be to use quantum repeaters, where we use entanglement to teleport the quantum state between two sites, as was mentioned earlier. Those intermediate nodes need no longer be trusted locations in quite the same way. And this approach does allow for more complex quantum computation, but these experiments are still in the sort of early days. So the trusted node model for QKD can be seen as a multi-layer model. So in this, we have separate QKD systems linked together, which are linking together adjacent trusted nodes, and each is independent from one another. They're point-to-point systems. And they keep building up caches of secure key material, and we can use this for transmission of data securely over those corresponding links. Sitting on top of that QKD is the key management layer, which is responsible for securely relaying end-to-end keys through the network, and does that using one-time pad encryption to relay a key generated at a source site in the network to the required destination site. And it has to do this using sort of authenticated one-time pad encryption so that we know we're talking to the right entities in this sort of network. The key is decrypted classically at each trusted node before being re-encrypted with that authenticated one-time pad to be relayed onto the next node in the network. And finally, we've got the secure application entities. These are things like the encryptors or the applications which takes the keys and makes use of them to encrypt classical data or so forth. And in that secure application entity layer, we're looking at the more like the end-to-end keys through the network. So that would, if we were going from site A to site C in this example, those secure entities would be requesting a key from site A to site C. But similarly, they could request keys for any points in that network. One of the key things in this is that we need standards to make sure all of this interops. So, for example, we've got the ETSI QKD 014 API standard, which is an example of a API that's used to exchange keys between the various entities in this example. So moving on, in a joint project between BT and Toshiba, which we launched in 2022, and we have built a commercial multi-tenanted quantum secured metro network across London. We've got 2 sites in the centre of London and 1 out on the west side in Slough, where a lot of data centres in the UK are based. We provide dedicated high bandwidth and low latency end-to-end encryption between these customer sites. So the encryption keys here are derived from QKD and combined with standard Diffie-Hellman key exchange within the encryptor. So we're taking in QKD derived entity and combining that with that standard Diffie-Hellman approach. We're also looking at PQC options, but at the moment we're sort of waiting for that standardization of those algorithms to complete. We've got 3 trusted node sites which are hosted in BT's core exchanges, and they're interconnected using dedicated fibers for the quantum channels. Customers connect to this using into our core exchanges using OpenReach's optical access products, and in those ones we have a shared fiber shared with both quantum and classical channels. And also, as part of this, we've integrated this into our management and operational network within BT. So just to give you a high-level diagram of the trial, we can see that sort of multi-layer diagram that we sort of showed earlier. So individual QKD systems link the core sites together and also the customer sites into the core. Sitting above that is a sort of KMS layer which allows the relaying of keys between the sites in the network using that authenticated one-time pad. Sitting on top of this is an optical line system for transmission of customer data from one site to another. And finally, the encryptors, which we're using AES-256 to encrypt the customer data in the trial as present, using a key derivation function which combines the keys distributed by the QKD and KMS layers with the key material established between the endpoints using Diffie-Hellman. And we regularly refresh those keys so that it's constantly getting new keys over time. So just to give you a few use cases from some of the customers. So we've got EY and HSBC on the network, and we can see a number of their press releases. HSBC recently running a simulated trading scenario over the trial network. Similarly, on the sort of right-hand side, you can sort of see a graph here showing the secure key rate which is in the blue, over one of our 12-kilometer access links in the network. Again, this is where classical and quantum channels coexist. This is showing at least 400 kilobits per second of key material being delivered across 8 weeks, and a corresponding very stable quantum bit error rate, which is shown in red. So there are many attack vectors in the security landscape across all the infrastructure in any network, and QKD can play its part in a number of those aspects. And really, probably its primary function is in the secure sharing of encryption keys that can be used to secure data in transit. And there are a number of other functions where QKD could have a more secondary function, which we're going to show in blue here. But really, we see that sort of QKD mostly playing a part in those two red aspects here. However, so I guess really we're saying here that QKD should be seen as a component within the wider sort of crypto security landscape. So when designing a quantum network, we have to make many considerations, and some of them are the same as classical networks, such as the installation process and the operations, although there will be some specific attention to the uniqueness of the quantum components. Some of the main things are the physical locations, due to the security of the equipment. However, that environmental factors, and in this we're sort of talking about temperature and things like vibration, may also need to be considered due to the sensitive nature of some of the optical hardware in these sort of devices. Standard APIs have to be made available to allow those layers to securely transfer key material and allow the interop between multiple vendors. What end service is provided is important to talking about the service level agreements, resilience, and how that allocation of key material can be distributed fairly across all the customers in a network, and whether you do sort of encryption or keys only type interfaces towards the end customer. And over the next few slides, we'll look at some of the security aspects of the quantum network design in more detail. So firstly, looking at the QKD implementation, and from a theoretical point of view, the QKD protocol can be proved secure through model-based security studies. However, in making a real-world practical implementation of a QKD system, it is possible to introduce vulnerabilities if this implementation is not done correctly. So the table here shows from ETSI some of the attacks that could be used against the typical QKD system, such as multi-photon emission or using light to gain insight into the device settings, but also lists the known countermeasures that the industry has found to protect against these. So work is still ongoing to understand the attacks and develop the appropriate countermeasures for QKD system implementations, and going forward that would sort of allow QKD systems to get a mark of assurance to show that they meet all these requirements to secure against these various attack vectors. But however, the entire system has to be secure and fit for purpose, including all of the components, quantum and classical. So that starts with architecture being produced and reviewed to ensure correct design procedures are being used. And one of those is really the hardening of those classical components, removing all those unneeded elements and protocols to minimize any attack surface. Segregating the key, secure keys and encrypted data away from the control management traffic is also key, with a lot of auditing taking place to ensure the overall system performance. Using the highest level of encryption for APIs and management is also important. Once complete, a reference model can then be produced of the full system to enable the offensive security testing to take place and check for vulnerabilities. Those then have to be fixed and patched, so that could be quite an iterative process, but best practice procedures such as CIS benchmarking can be used to improve this. A documented acceptance process for the system is also necessary. So once that reference model is validated, this can then be pushed out to the live network deployment. However, this process would always be considered a continuous process, so you'd then start going back to design to make sure that's updated, taking account of the best practice that's coming about, and also make sure the network is updated to patch new vulnerabilities. And just starting to conclude, there's a number of projects taking place on quantum network assurance. So Nostradamus, which was mentioned earlier, as sort of a consortium looking at that testing and assurance of the QKD links and infrastructures. The various standards bodies, ETSI, ISO, ITU, IETF, are all defining those APIs for those different components of network, quantum networks and overall control. Also defining the security models and correctness around quantum components and networks. Within the UK, there is a project called Quantum Link Assurance System, so looking at developing independent link validation systems to show how fibre-based QKD is performing. And finally, the call for action is to develop and road test the assurance methods for QKD already defined in all the various standards, whether that's ETSI or ISO. Develop system-level assurance methods for the system, including the QKD component, and increasing understanding of the QKD and quantum networks within the cyber security community, and vice versa. It's a two-way thing with how we have to get that learning. Getting involved is getting involved within the various standards bodies. Also trialing QKD if your organisation can do that. So very recently the BT-Toshiba quantum trial is now available to view on the AWS marketplace, or look at any other sort of joint research project you can do. And we've got a number of links to the various standards and standards groups down there. So thank you for your time, and that's me done.